In this lecture, we are going to discuss how to choose the final hyperparameter of the ARIMA model, which is P, the order of the AR component. This is accomplished by looking at the PACF, which stands for partial autocorrelation function. In my opinion, the partial autocorrelation function is a bit more difficult to understand than the ACF. However, the way that we apply it is the same as how we apply the ACF for the moving average model. So in this lecture, first we will just simply discuss how to use the PACF. Then we will discuss a tiny bit more about what the PACF actually is in case you are interested. You should not feel obligated to understand the second part in order to move on to the next lecture. So what is the PACF from a practical perspective? From a practical perspective, it's just a plot that looks very similar to the ACF in that it's some kind of autocorrelation function. The vertical axis is still the value of the function, and the horizontal axis still represents some lag. The way that we use it is exactly the same as for the moving average. There will be some confidence interval on the ACF plot. If we see any statistically significant non-zero lags up to some lag p, this would indicate that we have an autoregressive component of order p. For example, if the highest non-zero PACF value is 5, then we would choose p equals 5. As before, it's usually the case that the PACF values below 5 will also be non-zero. Alright, so now that you know how the PACF works, what is the PACF really? We know that it results in a graph that looks like the ACF, but it is clearly not the same, since it has a different name and a different purpose. There are two ways of thinking about the PACF. The first way is to simply look at what it is in terms of its definition. The second way to look at the PACF is to consider how it's calculated. Looking at both of these perspectives should help you understand the PACF. So what is the partial autocorrelation function? The partial autocorrelation function at lag tau is defined as the correlation between y at time t and y at time t plus tau conditioned on all the y's in between t plus tau. So that's y at t plus 1, y at t plus 2, all the way up to y of t plus tau minus 1. So one way to think about this is, it's like a conditional autocorrelation, whereas the regular autocorrelation is unconditional, in other words, not conditioned on anything. The second way to think of the PACF is how we calculate it. We usually define the PACF coefficients using the Greek letter phi, and we use double indices. So we'll have phi 00, phi 11, and so on. In general, these will be represented by phi tau tau. Note that phi 00 will just be 1 as usual. This is because this is the PACF between y at time t and y at time t for any t, and therefore there are no in-between values, and it's just the same as the ACF. Furthermore, the same thing happens for phi 11 because again, there are no values in between y at time t and y at time t plus 1. Therefore, this just reduces to the autocorrelation at lag 1. What about for any other tau? In this case, we need to do a few autoregressions. Specifically, suppose that y hat of time t plus tau is regressed on all of the y's in between t plus tau and t. Note that this is just our usual autoregressive model. Next, let y hat at time t be another regression, again based on all the y's, in between t plus tau and t. This one is weird because it's like a backwards autoregression. We are using future values to predict a past value. So both y hat at time t plus tau and y hat at time t are regressed on the same set of variables, the ones in between. Next, we have the big reveal. Phi at tau tau is just the correlation between y at time t plus tau minus y hat at time t plus tau and y at time t minus y hat at time t as defined on the previous slide. That is to say, phi at tau tau, or the PACF for lag tau, is the correlation between any noise after subtracting off the parts that could be predicted by the regressions. You may have to repeat this to yourself a few times, but it will make perfect sense. The partial autocorrelation function is just the correlation conditioned on the in-between variables. Therefore, it's the correlation between whatever we can't explain using those in-between variables. And of course, that makes perfect sense for choosing the order P in an autoregressive model. If the PACF is non-zero, that means there is a significant correlation that cannot be explained by the in-between variables, and therefore, we should include this correlation in our final autoregressive model. So just to put some real numbers to this, suppose that we want to know if y1 is helpful in predicting y5. Obviously, the same question applies to y2 and y6, y3 and y7, and so forth. This is because we assume our signal is stationary, and therefore any autocorrelations only depend on the time difference. But let's stick to y1 and y5. The in-between values are y2, y3, and y4. The PACF will be large if there is a large correlation between y1 and y5 that cannot be predicted by y2, y3, and y4. Therefore, we should use y1 in our autoregressive model for predicting y5. That is to say, whenever we see large values in the PACF, it indicates that these should be included in our autoregressive model.